Hello everyone, my name is Ryan Mather, and in this video I'm going to be giving a general introduction to what's called the regression discontinuity method. Now, this is a method often used by econometricians or statisticians that is very powerful. It's useful in a lot of different real-world contexts, but it's typically not covered in your standard econometrics or statistics sequence in undergrad. So there may be some of you who have had experience at different undergraduate level courses and are now curious, what's this next step? What's going on with regression discontinuity? You'll notice along the bottom that I have this disclaimer here. It says the conclusions of this research do not necessarily reflect the opinions or official position of the Texas Education Agency, the Texas Higher Education Coordinating Board, the Texas Workforce Commission, or the state of Texas. The reason for that disclaimer is toward the end of the video, if you make it that far, I will be sharing some data from my own research using data from the Texas Schools Project. And anytime you're using data from Texas, they just want you to clarify this is my opinion, Ryan's opinion, and not the opinion of Texas. In this video, I'm going to be assuming that you come with a little bit of background knowledge. Not too much, it's going to be a pretty general video, but I am going to assume that you know two things. So the first thing that I'll assume is that you are familiar with conditional expectations. So if you see notation like this, you should know this is the expectation of y conditional on some value x. So in the real world, this could be for perhaps what is the expected return on investing in Apple stock given that today it is rainy. So maybe you think that having it be a rainy day tells you something about whether Apple stock will be going up or down, and this expectation would capture that. For those of you who are kind of just starting out with expectations, you can think about an expectation just like an average, except it's an average over the full population. So that's the first thing I'm going to assume that you know. And the second thing that I'm going to assume that you know is that I'm going to assume that you know about multivariate regression. So if you see a line like this, you should be comfortable with that. You should have seen that before. And you should know that these parameters right here can be found by running a regression. Whether or not you can do that by hand, just knowing that it can be done is something that you'll want to know how to do for this video. Now in this video, I'm going to be relying a bit on the programming language Stata. If you're not comfortable in Stata or you prefer a different programming language, the concepts explained here will work in other languages as well. But if you do like Stata, if you have it downloaded, then in the link or in the description of this video, you'll find a link to a do file, which is going to go right along with these lecture slides. And show you the codes in Stata for reproducing some of the results that I show here. So hopefully you find that useful. All right, that's enough of an introduction. Let's get started here. One of the main problems that we face when we apply statistics to the real world is this. We're trying to find the effect of some kind of treatment. And a treatment could be anything that has an effect. Think medicine, think a government policy, or an educational intervention, something like that. And we want to know what effect that treatment has. In the ideal world, what we'd have is a large population of people, and we'd randomly select from that population two groups. And to group number one, we would give them the treatment, and to group number two, we would not give them the treatment. And then we would see what happens to both groups. Because those two assignments are random, at the end of the day, we'll be able to look at these two groups, and on average, the only difference between these two groups should be that we gave the treatment to group one and not the treatment to, we didn't give the treatment to group two. So the difference between these two groups will tell us something about the treatment effect. The problem in the real world is that ethics, resource constraints, and etc. can remove the randomness. So to go through some of those things I just mentioned, if we think about medicine, ethically, if we have a certain limited amount of medicine, say that we're going into a developing country and we have some malaria medication, ethically, we need to give that medication to those who are the most sick. But that creates a problem for evaluating the effectiveness of the malaria medication because we've given it to a group of people that's different than the group of people that we did not give the medication to, and so we can't just directly compare them. And you see similar problems with poverty assistance. They're given to those most in need, and educational interventions are done for students that are often struggling the most. You can think about all sorts of examples in the real world about, for some reason or another, the treatment that you're interested in looking in is not randomly assigned between these two groups. And like I said, that creates differences between the treated and untreated populations that are beyond just receiving a treatment. Now, you need to be able to describe the problem in this general of terms, but as econometricians, as statisticians, we'll want to go just a little bit deeper to be able to describe this in math so that we can make our ideas a little bit more precise. So to explain it in math, imagine that a person I's outcome is y, and then it's going to be one of two different things. Y0 corresponds to the untreated outcome, and we'll say that this is, for each person, some epsilon I. That epsilon I, you can think about it as just their individual characteristics. If you didn't give this person the drug, if you didn't give them the treatment, what are their individual characteristics going to lead to for that outcome? The treated outcome takes those individual characteristics and adds on some individual specific treatment effect. And so you'll notice that all of these are indexed by I. So the individual characteristics can be specific to an individual, and the treatment effect can be specific to that individual. And if they're treated, both of these two happen together, and we are left with the treated outcome. If that's how we're going to express it in math, the way that I look at the treatment effect is I take the difference between the treated group and the untreated group. So this is where you're seeing that conditional expectation I was saying we would need to know earlier. So this is the conditional expectation of your outcome, and you're conditioning on the fact that all of these individuals were treated. And over here, we're conditioning on the fact that all of these individuals were not treated. If we break this down using the notation we have above, we know that the treated outcome is your individual characteristics plus the beta term. And your untreated outcome is just your individual characteristics. Now, one other rule that you may know if you're familiar with conditional expectations is that we can always break up the conditional expectation around an addition sign. So I can take this first term and say this is actually the expectation of epsilon I, given that I was treated, plus the expectation of beta I, given that I was treated. And of course over here this is still the same for I not treated. We can break them up like that. And once we've broken them up, there's a way of reorganizing things that will help us to understand what's going on. And that is this. If we pull out that expectation of beta term out front, this is what we are generally curious about in the real world. It's the average treatment effect on the treated units. So what you've done is you've taken that treatment effect and you've averaged it across all people, and you're able to say this is generally what we would expect the treatment effect to be. It's the effect of the malaria medication, it's the effect of the poverty assistance program, or that educational intervention. The potential problem comes in this second term over here. This is the difference between the individual characteristics. Now, if we assigned these groups randomly, you would expect the individual characteristics to be more or less the same between the treated group and the untreated group. And as a result, this term up here would equal 0. Unfortunately, if the assignment into treatment and non-treatment was not random, then in general, we wouldn't necessarily expect this to be equal to 0, and in fact, it could be not equal to 0. And so what we're left with, if if treatments weren't assigned randomly, is that the difference between outcomes in the treated and untreated populations includes both the average treatment effect that we want and the difference between individual characteristics And we have no way of knowing how big these two components are. If we see a large difference between the treated and untreated populations, it could be coming from a large treatment effect, or it could be coming from a large difference in individual idiosyncratic characteristics, and we just don't know. That's the problem in math. Now let's get a little bit more specific and look at a real-world example of where this might come about. So I'm going to be taking this real-world example from the paper Cataneo et al. It's described in the references in this presentation, which we'll see at the end. And the problem is this. Imagine that you are some kind of a super PAC, or you are investing in different candidates around the country, and you want to know which candidate you should support for your party to win. And you have this question. If you want a candidate from your party to win in the next election for a Senate seat, how much does it help if your party currently holds that seat? So in other words, if your party has the incumbent in a specific election, how much is that going to help? If it really helps, maybe you don't need to donate as much money for the campaign. But if it doesn't help very much, this might be a harder race and you may need to donate more. From what we talked about earlier, you should be able to see what's wrong with this approach right here. If I compare the share of votes a party gets when they do and do not have an incumbent, where every individual I here represents a different election. So I could try and find this treatment effect by taking the expectation in voting shares where the party had the incumbent and the expectation in voting shares where the party did not have the incumbent. I could take the difference between these two. Now, if you want to pause the video here, think about how do I describe what the problem is with finding the treatment effect in this way. So I'll give you a moment to do that. My favorite way of describing what's wrong here is to think of two specific states within the United States. So let's imagine that we're talking about the Democratic Party. A state that has the Democratic incumbent is likely going to be a fairly liberal state. So maybe we could imagine it being California over here. And if we just go out and find places where the Democrat does not have the incumbent, that's likely to be a more conservative state. We could say, for example, Idaho. So in these two groups, we have generally more liberal states having the Democratic incumbent and generally more conservative states not having the Democratic incumbent. Just putting these two states up here, there's clearly a lot of differences between these two states beyond just which party has the incumbent seat in a Senate election. California has much different industries than Idaho, and just the broader culture, economic conditions, and so forth, which lead California to be liberal, are very different than similar conditions in Idaho, which lead them to be a little bit more conservative. And so if we take this difference, we're not going to be able to tell what part of this is coming from the effect of having an incumbent, and what part of this is just coming from differences in these two states, or in states where we see an incumbent or not an incumbent. To break this down, we're going to define for the next slide the Democratic winning margin as the share of votes that were for Democrats minus the share of votes that were for Republicans. So on the next slide, you can see that. The Democratic winning margin is right here along the x-axis. This is the share of votes that were for Democrats minus the share of votes that were for Republicans. The rest of the graph is fairly complicated, but we'll go through it slow. Let's break it down. On the left-hand side, this axis gives the share of votes that were Democratic in the current election. So the x-axis is the Democratic winning margin in the previous election. The y-axis shows the share of votes that were Democratic in this election. And what I've graphed here is imaginary data that you will never have access to in the real world. What I have is two dots for every single election. The red dot shows what would happen if that party did not have the incumbent. So this is the untreated outcome, the Y0I. And then the blue dot shows what would happen if that party did have the incumbent. So this is the treated outcome, epsilon I plus beta I. This is the treated outcome. Now, of course, you're never going to see both of these in the real world because it can't be that for a specific election, your party both has the incumbent and does not. But imagine with me for a moment that we did have access to this data. If we did have access to this data, then finding the treatment effects would be very easy. I would just take this data point up here and subtract the data point down here. And this difference between these two data points would be the treatment effect for that election. I could also find the treatment effect over here. I could find the treatment effect over here, go a little bit further. And if I wanted to find an average treatment effect, I could look over all of the different elections, add them all up, and take this sample average of this treatment effect. That would be what I would do if I had perfect data. Unfortunately, I don't have perfect data. I'm only going to observe either the treated outcome or the untreated outcome. And specifically, I'm going to see this. So remember, the Democratic winning share in the last election is the share that went Democrat minus the share that went Republican. That means that everywhere where this is positive, the share that went Democrat was greater than the share that went Republican, and the Democrats won. Because they won, they have the incumbent, and what we see is the treated outcome for everywhere right of this zero. For everywhere to the left of this zero, in this case, the share of votes that went Democrat minus the share of votes that went Republican is less than zero. The Republicans won this election, and the Democrat does not have the incumbent. So we're dealing with lots of untreated outcomes over here. This is what we have. And the last thing that I'll mention on this slide before we kind of get to the regression discontinuity portion of this is that the lines that I've graphed here show the averages. So this line gives the average of these data points over here, and the red line to the left gives the average over there. The way that we've prepared this graph suggests what the regression discontinuity solution to this problem is going to be. Notice that over here, I can't compare treated and untreated outcomes. I just don't have the untreated outcomes. And over here, I can't compare them because I just don't have the treated outcomes. But there's this one space right in the middle where you effectively are able to see both the treated outcome and the untreated outcome very, very close together. So the intuition of the regression discontinuity method is that, hey, if I take the difference between the average above and the average below, this is going to be a measure of the treatment effect. Right there. And it's the local treatment effect in the sense that it's local to this area of variation. It's just in this specific spot we found the treatment effect. If you understand this slide, you understand the logic of the regression discontinuity method. And that's the beautiful thing about the regression discontinuity method, or one of the beautiful things, is that it is very simple to convey visually. As you guys go further in your careers, you'll be able to pursue more and more econometrically advanced ways of dealing with different issues in the data, and you can devote more and more time to eliminating all the issues. But at the end of the day, you're going to have to take your project and take it to people who have not spent as much time in the data as you have, haven't spent as much time thinking about the problem as you have. And so in order for the results that you've received to make any difference in the real world, you're going to have to take them and explain them in a way that people are going to get quickly. And with declining attention spans, frankly, I'm amazed that you've made it this far in the video. With declining attention spans, people aren't typically going to have this long of a time to think through different things. So visual arguments for why your estimation strategy works are going to be very powerful, and the regression discontinuity method gives you just that. There should be no meaningful difference between elections just to the left of this line and elections just to the right of this line. On average, they should be the same. The only meaningful difference is that just to the left, the Republicans won, and just to the right, the Democrats won. And so by comparing them, we can get a sense of the incumbency advantage and its effect on the share of votes that will be Democratic in this election. Now, what I was showing you in the previous slide is entirely fake data. Now what I'm going to do is show you real-world data. You might have noticed, for example, that some of these vote shares go above 100%. Obviously, that wouldn't happen in the real world. What I'm showing you here is real-world election data. And if you follow along with this data do file, the code is there that's necessary to download this data and then make the graphs that I'm showing you here. This first graph just gives the raw data. So every single one of these dots represents an election. It's difficult from the raw data to really get a sense of what's going on. So the first thing that I'm going to do is I'm going to divide this data up into bins. Maybe I'll say this is bin 1, this is bin 2, this can be bin 3, so on and so forth. And within each bin, I'm going to take the average of the data points in that bin and plot just the average. So here, maybe the average is over here. Maybe for 3, the average is right there. And this is going to help us to simplify this graph with all of these different dots. When I do that, this is the picture that results. And again, for all these things, you can see the code to do it in the do file in the description underneath this video. So you can see now that we removed some of the noise, it's a little bit clearer what's going on. It does look like there's some kind of a gap between the places where the Democrats have just barely won the election and the places where the Democrats have just barely lost. To make that gap easier to see, we might put an average line on each side, like I had done in the previous slide. And specifically to make this average line, what I'm going to do is run a regression on the left-hand side and the right-hand side. So on the left-hand side, I'm running some kind of regression like this, where X is the Democratic winning margin. In regression discontinuity, we often call this X the running variable. And on the left-hand side, I'm running a regression. You can do that, and this is what it looks like. So now I have the difference between the line over here and the line over there. And I can say that this is an estimate of the treatment effect associated with having the incumbent elected. Now you might say, well, this is all well and good, but this looks too simple as a way of taking the average on the left-hand side and on the right-hand side. You know, maybe the line should come down a little bit more here, and maybe the line should go up a little bit more there. If we want to have a more complicated or a better fit of this average on either side, we can do that with a more complicated regression on each side of the line. So on the left-hand side, both of these regressions are quartics. And what that means is that the highest power in the regression is raised to the 4th. The highest power is 4. Or you might also hear that this is a polynomial of order 4. So what we've done on the left-hand side is fit a regression. So we've fit different beta coefficients over here. And we got this resulting line that you see here. And we can do the same thing on the right-hand side. And this line fits the data points now a little bit better than it had previously. You can see again, we can take the difference between these 2 points, and this will give us the treatment effect. So remember, one of the strengths of the regression discontinuity method is that it is very visual. So if you are in the C-suite of your company, you're presenting to a politician, wherever the final stage presentation of your results is, you're going to give kind of a 1-2 punch. The first thing that you're going to show them is a picture like this. And you're going to say, look, the differences on the left-hand side and on the right-hand side, on average, the only difference should be the incumbency effect, because we would otherwise expect that these two groups are on average the same. And then you'll show some kind of a table with an estimate for what this treatment effect is. So the table might look something like this. You've got your RD estimate, and we are estimating that the treatment effect is 10.58. In other words, if you have the incumbency advantage, you can expect in the next election to have a vote share that's 10.58 percentage points higher than you otherwise would. So the incumbency effect is a very large advantage that you have in elections. What I've put along the top here is the stata command needed to make this happen. So we're going to be using specifically the package RD Robust. There are different packages that you can use to run RD estimates. The first thing that we put is the outcome variable. So vote is representing the vote share Democratic in this election. And the second thing we put is the running variable. Remember, that was our X variable from before. So margin is the Democratic winning margin in the previous election. And what I've done with the rest of these options is communicated to Stata some of the things that I want for how to estimate things on the left-hand side and on the right-hand side. You remember from the last graph that we had a polynomial of degree 4. And so I specify that here with this P4. And what this is doing is it's specifying something called the bandwidth on either side of the regression. So if we go back for just a moment, all the magic of the regression discontinuity method is happening right here, right around the cutoff. And so ideally, you would only include data very close to that cutoff. If you have sufficient data, it's best to include data right around that cutoff, because that's the area where you're getting this very clean split of the treatment effect just to the right of the cutoff and the untreated effect just to the left of the cutoff. So what people will do is they'll specify some kind of bandwidth. They'll say, I'm only going to use data on the left-hand side up to, say, 30. So this would be negative 30. And I'm only going to use data on the right-hand side up to, say, positive 30. I only use the data in this window to fit the quartic polynomial. That's what I've specified in the H3030 option that you see on the next slide. I'm saying disregard all of the data except the data that fits within this range on the right-hand side and this range on the left-hand side. And the last option that you might commonly use with RD Robust that I didn't have to use here is you will put a C at the end, and in that C you'll put the place where the discontinuity happens. In this case, I didn't need to put it there because the discontinuity happens at 0, and RD Robust assumes by default that this discontinuity happens at 0. Now, if you're running this, if you have the do file, I would recommend playing around with it a little bit, making sure that you understand what's going on. And you'll notice that if you don't include any options over here, if you don't include the order of the polynomial, and if you don't include the bandwidth to the left and to the right, Stata will do something by default. It will do some kind of algorithm to set what it thinks the order of the polynomial should be, and it will do some kind of algorithm to say what the bandwidth should be. If you want to see what those algorithms are and the way it's doing it, you can type in help RD Robust and look in the help file, get a little bit more into the weeds there. For the purpose of this introductory video, we won't be going there too much. One last thing that I want to draw your attention to on this slide is, remember, with the bandwidth, what we're saying is that we're only going to use data that's 30 to the left and 30 to the right. The cost of doing that is that you've not used a lot of your data. So that's shown down here. The total observations that we have in our data set is 1,297. The effective observations is 474 on the left and 457 on the right. What does that mean? It means that if I've got my margin graph over here, there was lots of data all over the place on the left-hand side, and there was lots of data all over the place on the right-hand side. But to fit that polynomial on the left-hand side, I restricted myself to the data just in this range of 30, and that gave me 474 observations on the left. And on the right-hand side, I restricted myself to this range up to 30. That gave me 457 observations on the right. So the more narrow you make your bandwidth, in some sense, the more accurate you're getting, because you're getting closer to the region where the discontinuity happens. But the trade-off is that the more narrow you make your bandwidth, the less of your data that you're able to include. And so you'll want to experiment a little bit and make sure if you change the bandwidth in different ways, it's not affecting your results too much. And you may just want to allow Stata to do the default method if you're unsure. So again, backing up a little bit, if you are showing this in the C-suite or to a politician or anywhere, you give your 1-2 punch. You show the picture from the last slide, you show this table, and then you stop right there. And that's good enough. You've given an estimate and you've given a very clear visual argument for why this estimate should be believable. As econometricians, we want to go a little bit deeper yet and think about how we can mathematically evaluate some of the assumptions that we're making in this process to really make sure that we're doing the right thing. Because we have a responsibility. When we're going into these different settings, it is possible, we all know it's possible, to manipulate these results in order to get something that either we want to see or our audience wants to see or what have you. And so in order to protect ourselves against that, we want to make sure that we're following the best practices, that we're really making sure that when we're doing this RD method, that we are doing it in the right way. And so you as the econometrician have the burden to keep watching in the video. Your audience will have stopped right here. So we're going to go a little bit deeper, and we're going to have one theorem for this PowerPoint. You always have to have one theorem in a good lecture. But we're going to use the same kind of notation that we had earlier. The treated outcomes are going to be the individual idiosyncratic characteristics plus some treatment effect, beta I. And then the untreated outcomes are going to have this just individual treatment effect. So treated outcomes, individual effect plus the treatment effect. Untreated outcomes will just have the epsilon term. In order to have a regression discontinuity problem, you need to have some sort of a running variable z. That's what's going to go along the x-axis. And you need some cutoff c. And the core assumption of a regression discontinuity design is that you have a cutoff at that c. So people with a running variable greater than the c or equal to the c get treated, and the rest of people do not. And that can allow you to rewrite the outcomes in a simpler way if you'd like, and we'll return to this indicator function a little bit later. Just to reiterate, we saw that this can exist in politics, but this kind of setup exists all over the world. And maybe once you're done watching this video, as you're making your way out and about, you'll start seeing all sorts of places where the regression discontinuity method can apply. Some examples are, imagine grade cutoffs for scholarships. Imagine that if you earn a 3.5 GPA, you get some kind of a scholarship. Well, there's really no meaningful difference between someone with a 3.499999 GPA and someone that barely got the 3.5. But there is a big difference in whether they receive the scholarship. And so we can look at that difference right there to evaluate the effect of the scholarship using the regression discontinuity method. You might see places where hurricane relief money is given to those with damages to their home over some level. Or in sports, if people run a marathon faster than 3 hours, 6 minutes, 51 seconds, they qualify for the Boston Marathon. Especially if you don't have some kind of clock standing up so people are super aware of their time. A person who just barely doesn't make that cutoff versus a person who does probably is about a similar level of athlete. But there's going to be a big difference in terms of whether or not they qualify for this higher level marathon. So that is the basic setup of a regression discontinuity design. Going forward, we need to make some additional assumptions to make sure that the regression discontinuity method is going to work. These two assumptions look fairly complicated, but they're not that bad. What both of these are saying is essentially that the untreated outcomes and the treated outcomes don't jump around the cutoff. And why do we need to assume that? Well, if you had the untreated outcomes over here and the treated outcomes over here, but imagine again that we're back in that world where we can see the untreated outcomes on both sides of the cutoff. Imagine that there was a jump in individual characteristics just to the right, so that the individual characteristics jumped up here. If that was true, then when I take my regression discontinuity estimate, I'm taking the difference between these two things, and I'm comparing people who are treated with people who are untreated, but I can't tell as the researcher what of this total difference I've estimated is coming from the treatment effect versus just the differences in individuals. So if this is the untreated outcome and this is the treated outcome up here, part of the difference that I'm seeing is coming from the treatment effect. Part of the difference is coming from differences in individuals. And so I'm again back to this same world where there's more to the differences between the treated and the untreated people than just the treatment effect. And so the method does not work. Now, one place where you'll often worry about this in the real world, or you'll hear about a concern with this, is people will talk about the word running variable manipulation. This is a common vocab word that we want to think about when we're talking about RD designs, because it's one of the ways that you might fail this test of the individual characteristics or the treatment effects being continuous right around the cutoff. So let's look back at our example and think about what running variable manipulation would look like in this case. Now, this was a very controversial issue in the United States a couple of years back. So I'm not saying anything about real world politics whatsoever. We're purely in the realm of statistics and econometrics. But the way running variable manipulation would occur in this context would be either voter fraud or election fraud. And here's how that might work. Imagine that these elections over here, the people counting the votes noticed, hey, we are just barely losing this election. And as a result, we can fudge a few ballots. We can put a few more ballots in that were Democratic, that weren't really Democratic, and just barely move ourselves over this cutoff to the other side. And similarly, you could imagine that this election does that, and this middle election does that. These elections are able to move over to the other side. Once that kind of effect has happened, you might see something like this. So those high dots on the left-hand side have moved over here and are high dots over here. And that's also created some higher dots over here, because remember, the treatment effect is whatever your individual characteristics are plus the treatment effect. So what I would do if I were coming through and doing an RD is you take the difference between this side, and that would be my RD estimate. But this is not actually an estimate of the treatment effect. On the left-hand side, the treatment effect brings you from these blue dots to the red dots. So this is the left-hand treatment effect. And on the right-hand side, the treatment effect goes from these blue dots down to the red. This is the right-hand treatment effect. And what I've estimated is neither of those two. It's much bigger than both of them. So this overall treatment effect that I estimate is not a proper treatment effect either on the left or the right. You're not really identifying anything. Now what I would recommend is to pause the video right here and think about how you would go about checking to see if this problem exists in your data. So I'll give you a second, pause the video, think about how you would solve this problem. If you've thought about it for a little bit, you've probably noticed that this is a fairly difficult problem to solve, because if you have real-world data, all that you have access to is these red data points on the left and the blue data points on the right. You don't have access to all these things that I've made a little bit dimmer here, the treated outcomes on the left or the untreated outcomes on the right. And because of that, it's really hard for you to tell if manipulation is going on just based on looking at this graph. For example, it could be the case that the treated outcomes on average really do go up like this. And it could be that on the left-hand side, the untreated outcomes really go down like that. So just the fact that you're seeing these odd dips on the right-hand side and on the left-hand side don't necessarily mean that there's anything wrong with the RD strategy. And similarly, if I had flat lines on both sides, flat lines could also result from some kind of running variable manipulation, just moving the lines in a slightly different way. And so just looking at these outcomes is not going to be enough to conclude if you have any sort of running variable manipulation. Now, thankfully, people have thought about this a long time, and there are ways of checking to see if running variable manipulation has occurred. You won't know for sure, but there are ways to check to see if there is any evidence of it occurring. One way of checking relies upon some intuition that you might have gotten earlier on when we were talking about these data points moving over. If data points just move themselves slightly to the left or slightly to the right of the cutoff, what you would expect if that has occurred is to have a bunch of extra data points over here on the right. So a lot of these data points from the left would have moved to the right, and you would expect to see a larger share of data points off to the right. So if I were to make a histogram, so I do a histogram of the data on this side, not great bars, but you understand what I mean. If there was some sort of running variable manipulation going on, I might expect the density to jump quite a bit on this right-hand side, because a lot of the variables, a lot of the individual elections would have just barely moved themselves over that line. And I might expect to see a jump there. So what we can do, one thing that we can do to test for running variable manipulation is we can look at the histogram and see, does it look like the histogram is jumping? So here's a graph showing that for the specific election data that we have. And the p-value I've shown here is testing if there is any meaningful difference between these averages on the left-hand side and on the right-hand side. This p-value of 0.381 is not in the typical region where we would reject the null hypothesis. And so instead, in this case, we're able to, we fail to reject the null hypothesis, and we're left saying there likely is not any sort of difference between the left-hand side and the right-hand side. So if you do this test, you get a p-value outside of the normal region with which you would reject a null hypothesis. That's strong evidence that there likely hasn't been manipulation of the sort where a bunch of these observations are moving just slightly to the right of the cutoff. But there are other things that you can do to test as well. You might have heard in your other classes about the idea of a balance test, where we're comparing two groups and we want to make sure that their characteristics match. In this case, our two groups are those just barely to the left of the cutoff and those just barely to the right of the cutoff. And what we're really interested in at this point is unaffected variables. So things that should not at all be affected by having the incumbency advantage. In our case, that might be things like the state population, or the percent of the population that's Caucasian, or the percent of the population that earns some income above some threshold. Those things don't necessarily change automatically when the Democratic Party has the incumbent. Or certainly things like state population. Usually you're not going to change states because your party has won or lost the election, unless you're really a diehard. And perhaps if you're really worried about that, you can measure the state population in the year before the first election happens. In any case, your job when doing a balance test is to go out and find things that you think should not be affected by the treatment. And then what we're going to do is basically run the RD test again and see if there's a difference between the left-hand side and on the right-hand side. So what I've done here is I've graphed the state population around this Democratic winning margin. And if there were to be a large difference here between the left-hand side and the right-hand side, that would again point to a failure of our assumptions. It would point to the individual idiosyncratic characteristics being different on the left-hand side and on the right-hand side. In this case, we cannot say that there's any sort of difference here with any sort of certainty. The p-value on this difference is also outside of a range where we would normally reject the null hypothesis. So in this case, we think there likely is not a meaningful difference between these two lines, and we pass our balance test. Those are the two ways that you can test to see if running variable manipulation or something like that is going on with your regression discontinuity design. Once you have those assumptions in place, the theorem is very simple. It just says what we've been saying before, although you might not recognize this notation. So what this notation means is that we're going to get the running variable really close to the cutoff from the right-hand side. That's what this plus means. And the notation over here means that we're going to get the running variable really close to the cutoff from the left-hand side. And then we will take the expectation and subtract the two. So this is showing in math the same thing that we've been talking about in words. You've got your dots on the left-hand side, you've got your dots on the right-hand side. And what the regression discontinuity method is going to do is it's going to take the expectation as we get really close on the left-hand side. It's going to take the expectation as we get really close on the right-hand side, take the difference between these two, and that should be the expected treatment effect right at the spot where Z is equal to the cutoff C. That's a powerful theorem. It's adapted from Han et al. If you want to look at that paper, I've included it in the references at the end of this video. It goes a little bit more into detail, and we'll touch on some of that detail later on if we have time. So that's the theorem. That's the main result behind the regression discontinuity design. And hopefully going through that has helped you to understand what exactly it is that you're assuming when you're running a regression discontinuity test. Now, some of you, and I respect you for this, are a little wary when I gave you that RD robust command, because you say, look, Stata is going to be doing potentially a lot of things in the background where I don't know exactly what's happening. Instead, give me something that I can just directly code up myself fairly easily. I want to understand every single step of the process. Awesome. So the simplest way to implement an RD regression is to simply run this regression line that I have shown at the top here. So this regression line involves a constant, like you're probably used to, a slope term with the running variable, and then there's this indicator function. So this indicator function is going to be 1 if zi is greater than or equal to c, and it's going to be 0 if zi is anything less than c. And then of course there's some noise here, but that won't factor into the way you estimate the regression. Remember, there's also this bandwidth to worry about. And so what you'll do is you'll run this regression on a subset of your data corresponding to the bandwidth that you want. So maybe you want, in the previous example, maybe you want 30 percentage points to the left and 30 percentage points to the right. You run this regression on a subset of your data that's within that bandwidth. And what you might get if you were to graph it is something like this. So this y-intercept right here, you estimate that with your beta 0 term. The beta 1 term is giving you the slope on the left-hand side and on the right-hand side. Now, it's certainly possible to estimate different slopes on the left-hand side and on the right-hand side. If you wanted to include a different slope on the left-hand side, you could add some kind of beta 3 term over here. So beta 3 ci, and then also multiply that by this indicator function. And you can do that just fine. In fact, you can make the line as complicated as you like on the left-hand and on the right-hand side. You can include all sorts of powers. We could have beta 1x, beta 2x squared, beta 3x cubed. That's fine. You can make the line as complicated as you want. No matter what, the key coefficient that you're going to be interested in is this term, the beta hat 2 term, and that's going to be estimating this difference right here between the left-hand side and the right-hand side. So the beta hat 2 is our estimate of the difference between those two sides, and it is our estimate of the treatment effect associated with the treatment that occurs right at the cutoff. That is the simplest way to implement a regression discontinuity design in your own framework using just the regression model that you are used to. So let's take a pause here and give a high-level overview of where we've been. Think about the pros and cons of the regression discontinuity method, because it's cool to learn about a new method, but ultimately we'd like this to be useful, and that demands knowing when to use it and when you should not. We'll give two of the pros first, and we've been talking about this throughout this time. One of the main pros of the regression discontinuity method is that it is visual and easy to explain. You want to be able to walk into your boss's office or the politician's office and put something visual up on the board, something that they can't forget, and something that's very easy for them to understand. On the other hand, even though you've made it visual and easy to understand, you haven't sacrificed much on rigor. It's true. It's not just an intuitive argument, it's a true argument that if you've got some kind of continuous running variable and you're looking just to the left of that variable and just to the right of that variable, oftentimes there's going to be no meaningful difference between the groups on the left and the groups on the right when you're looking at the averages, besides the fact that the group on the right has received this treatment. And so it is a very highly rigorous way of measuring a treatment effect. If I were to list some of the main cons, I think the absolute first con is that you don't always have data or a situation where the regression discontinuity method can apply. If treatment doesn't occur at a cutoff, the regression discontinuity method is just not going to work. Remember from earlier, the regression discontinuity method will work in a lot more context than you might initially think. Once you learn how to look for them, cutoffs are all over the place in the real world. But of course, they don't exist everywhere, and that is a substantial limitation. The other limitation is that it's going to require a large amount of data right around the cutoff. So the core of your argument when you're doing a regression discontinuity design is that just to the left of this line and just to the right, there's no meaningful difference. So ideally, you're going to be using data just barely to the left and just barely to the right in order to make that estimation. But remember from when we were talking about effective observations on the left and effective observations on the right, the smaller that I make that bandwidth, the fewer the observations right here that I'm going to have access to. And so in order to do the regression discontinuity method accurately, you're going to need large amounts of data right around the cutoff. The next con is definitely a con, but it's not quite so bad as you might think. So the con is that we are only estimating this treatment effect in a small local area. Specifically, we're estimating the treatment effect right here around this discontinuity in the middle. Find my pen. Right around this discontinuity right here. Nowhere else. We're not finding the treatment effect over here to the right, and we're not finding the treatment effect over here to the left. We're just finding the treatment effect in that very narrow spot. And so if you're in some kind of situation where you need to be able to estimate things far away from the discontinuity, the regression discontinuity method is not going to be a great option for you. One way that I'll still defend the regression discontinuity method, though, is that oftentimes the effect is identified in an area that is usually quite relevant for decision making, or it may even be the most relevant area. And the reason for that is that these cutoffs are often arbitrarily selected by humans who can change that policy in the future, and we're often wondering whether the policy should be changed or not. So imagine that we are in the scholarship context, and we are going to be giving scholarships to people with a GPA over 3.5. And then imagine that our outcome variable is something like lifetime earnings. So if you get the scholarship, maybe you're able to go to college, and we would expect your lifetime earnings to increase. With the regression discontinuity method, we're not able to identify the influence of the scholarship on those with GPAs very high, say 4.0. And we're not able to identify it over here with low GPAs, but we are able to identify it for GPAs right around 3.5. The reason that's perhaps the most useful place to find the treatment effect is that right there, the 3.5, is the treatment effect at the person who is marginally qualifying for this scholarship. And we could imagine that the treatment effect is likely going to be quite similar if we move slightly to the left or slightly to the right. And so if a policymaker is looking at this GPA cutoff thinking, well, should we make the GPA cutoff slightly higher or slightly lower, the regression discontinuity estimate gives them a strong understanding of what benefits they'll be sacrificing by moving the cutoff to the left, or what benefits they'll be gaining by moving the cutoff to the right. Actually, I may have given that in reverse, but you understand what I mean. We have an understanding of the benefits and the costs right around the cutoff, which is the most relevant area for the policy maker. The very last con to be aware of is that you need to be careful about running variable manipulation. But again, here we have tools so that this isn't quite such a big deal. You can do your McCrary style density tests, and you can do your balance tests. And with those two tests, you can be confident that running variable manipulation isn't affecting things too much. So this was a broad level overview of the regression discontinuity design. If you have a little bit more time, with these slides, I'll go just a little bit deeper and talk about my favorite extension to the regression discontinuity design called the fuzzy regression discontinuity design. The reason why this is my favorite extension is that it's going to greatly expand the amount of areas where the regression discontinuity method can apply. Remember from before, in order to apply the regression discontinuity method, we needed a context where there were no people that were treated to the left of the cutoff, and everyone was treated to the right-hand side of the cutoff. But there are lots of places in the real world where there is some kind of a cutoff, but it's not that dramatic. It's not everybody untreated on the right and everybody treated on the everybody untreated on the left and everybody treated on the right. Maybe it's just some difference in the probability of getting treated. So some examples of that are, imagine that we're interested in the effects of college acceptance, and college admissions officers give a second look to applications with GPAs 3.5 and above. In this case, there are going to be people that are accepted that have a GPA just barely to the right of 3.5, and there are going to be people that are accepted with a GPA just barely to the left of 3.5. But there is something that changes at that 3.5 GPA, and that is that the application gets a second look. And so the probability of gaining college acceptance goes up right at that GPA of 3.5. To use a medical example, let's say that we're interested in the effect of a cholesterol medication, and physicians are supposed to recommend the medication when a patient has a total cholesterol level at or above 240 milligrams per deciliter of blood. Again, the person that has just 239.99999 as their cholesterol level is probably not meaningfully different than the person with the cholesterol level just barely above 240. However, there is going to be a difference between these two people, which is that the physician will recommend it to the person just to the right, and they won't recommend it to the person just on the left. Now, the people on the left and on the right are free to take the cholesterol medication. They can go out and buy it. And so they may do that whether or not the physician has recommended it, especially if this is something that maybe you don't need a prescription for. But there is definitely going to be an increase in the probability of receiving that medication right around that 240. With the fuzzy regression discontinuity design, you have the same advantage from regression discontinuity, that it's going to be a highly visual argument. Unfortunately, the visuals are slightly more complicated. You'll need two graphs rather than just one. So the first graph that I'm showing you here has a y-axis, which is the probability of getting treated. And this is fake data, totally made up. But in this fake data, the probability of getting treated jumps right at 50. So this is the core assumption that you need in order for a fuzzy regression discontinuity method to work. You need there to be some kind of a jump in the probability of getting treated right at a cutoff, which in our case is 50. So what's going to happen to the outcomes at that cutoff? Well, imagine over here that the blue line gives us the treated outcomes, and the red line gives us the untreated outcomes. And then imagine that all these green dots are individual data points that we see in the real world. So down here, where the running variable is close to 0, the probability of being treated is quite low. And so all of these green dots are clustered around the untreated outcome, this red line. On the far right-hand side, it's just the opposite. So the probability of being treated is very high, and so all these green dots are clustered around the treated outcome. And in between that range, the probability is changing. So this green line is plotting the average of the green dots all along the running variable. And you'll notice that because the probability of being treated jumps at 50, that is going to create a jump in the outcomes over here. So there will be a jump in outcomes, but you can tell that that jump in outcomes is not the same as the full jump in outcomes that constitutes the treatment effect. So this is the full treatment effect. And then the jump in outcomes that we observe is this smaller portion, which I'll label B. What the regression discontinuity method does, and I don't know if this is intuitive to you or not, maybe for some of you it's intuitive, but regardless, it's a beautiful result. The regression discontinuity method tells us that the treatment effect, which we can write as the expectation of beta I, right where the running variable is equal to C, that treatment effect is equal to the difference in the outcomes divided by the difference in the probability. So it's this B that we've identified, and it is then divided by this A that we have identified. The logic is much the same as it was in the just standard regression discontinuity method. There's no meaningful difference to the left of 50 and to the right of 50 beyond that the probability has changed. But that probability changing is giving us what we can call exogenous variation in whether or not people around this cutoff have been assigned to treatment, and we can leverage that variation to get a great estimate of the treatment effect right here at the spot where the running variable is equal to the cutoff. So we'll briefly just mention here that the Han et al., if you go to that paper, the full version of their theorem covers this fuzzy case. And for this introductory video, I won't go over the details of that proof. But you can see that the result is just what we've said down here. So We're introducing this new variable D, which says if a person has been treated or not. And so what we expect D to be, this is just another way of saying the probability of being treated. Do you expect D to be 1? Well, that's a probability of 100%. Or if we're very confident that D will be 0, that's a probability of 0%. So we're taking this probability, that's the denominator, and then for our numerator, we're taking the difference in outcomes just like we had before. And that's going to identify this treatment effect right here. Now, some of you have even more intuition from econometrics. Maybe you went further than just multivariate regression and you even began thinking about two-stage least squares or instrumental variables. If that's you, you may have some extra intuition for what's going on here from instrumental variables. So you can think about it like a two-stage equation where the cutoff in the probability of treatment is your first stage, and then there's some second stage where that treatment is then going to be affecting the y variable. Of course, I didn't tell you that you needed to know instrumental variable regression at the beginning of this video. So this is not at all required to really understand the fuzzy regression discontinuity method. But if you do have that background in two-stage least squares, hopefully this is helpful to you. So let's head on back. For this time, I'm going to give an example from my own research. And this research is still in process, so the results are likely to change. But it's a good way of explaining a case where you might see the fuzzy regression discontinuity applying in the real world. So our example has to do with the Texas Public Education Grant. The Public Education Grant is a program in Texas designed to encourage students to transfer away from low-performing schools. So the way it works is that low-performing schools can be placed on something called the peg list. And if you're placed on the peg list, or if your school is on the peg list, all of the parents get notified that the school is on the peg list. That's like stage number 1 of the treatment. Everybody's notified your school is low performing according to the state standardized tests and the various things that can land you on the peg list. And then stage 2 is that those parents that were notified are free to transfer their students to other districts as a PEG transfer. The advantage of being a PEG transfer is that the receiving district will receive some extra funding. So you're required to transfer from a PEG listed school to a school that's not on the PEG list. But once you do that, the receiving district will receive some extra funding, and the idea of this whole program is to try and get students away from these low-performing schools and transfer them to higher-performing schools. Now, there are multiple ways to get placed on the PEG list. One consistent way is if you're having a failing rate on a state standardized test above 49.5% in 2 of the last 3 years. And the state standardized test that they're using for this rule might change from year to year, but this is a consistent rule. If you have a failing rate above this 49.5% in 2 of the last 3 years, then you are going to be placed on the PEG list. So if you want to, again, you can pause the video right here. Think about how you would design a regression discontinuity method in this case, or a fuzzy regression discontinuity method in this case. But you likely didn't have to think too hard because the example or the answer is right there at the bottom of the slide. So what we're going to do to use the fuzzy regression discontinuity method here is we're going to limit our sample to schools that had a failing rate above 49.5 in 1 of the last 2 years, just 1 of them. Then we're going to look at this year. And if those schools have a failing rate above 49.5% in this year, then they're placed on the PEG list. So we're only looking at schools that were on the PEG list in 1 of the last 2 years. For all of those schools, if they fail again this year, they're going on the PEG list. So that creates a discontinuity. If you just get over 49.5% failing this year, you're going to go on the peg list. However, it's a fuzzy discontinuity because there are people that are going to be on the peg list even if they don't fail, because there are lots of reasons that you could be put on the peg list. You could be put on the peg list for a number of other reasons. And so this is a fuzzy regression discontinuity. It's a jump in your probability of being placed on the peg list. And it's going to happen right at 49.5%. Okay, all of that is background. And if that was a little bit too quick for you, I'll place a link to the paper in the description if you're really interested. But the main reason I wanted to bring out this example was just to show you what these graphs look like with real-world data. So what I've shown here on the left-hand side is this graph of your probability. So the left-hand side, the left axis, is the probability of being placed on the peg list. And you can see that even for those where they did not fail, up to 49.5%, they still have some probability of being placed on the peg list. But there's a clear jump so that those which did have a failing rate above this place are getting placed on the peg list at a much higher frequency. So this jump right here is our A. It's our denominator. And then we can look at different outcomes. One outcome that you might be interested in is the maximum failing rate in the year after the peg list was announced. Schools that are placed on the peg list have an incentive to respond and improve their standardized testing scores so that they don't get placed on the peg list again and they don't have this potentially embarrassing email or embarrassing letter sent out to all the parents of their students. They want to get off of the peg list. And so they may, through whatever method, do something to improve their test scores the next year. Maybe they devote more classroom time to improving the things that are tested, or they do things like that. We do see that there is a jump in the averages between the left-hand side and on the right-hand side, where the failing rate goes down among schools that were placed on the peg list, which is exactly what you would expect. If you're placed on the peg list, you have an added incentive to improve your standardized test scores so that you don't get on the peg list again in the future. So the treatment effect, just like before, the expectation of our treatment effect right at the cutoff is going to be this B divided by A. So that's all for this presentation. Hopefully it was helpful. We covered not only the regression discontinuity method, but an extension to it called the fuzzy regression discontinuity method. There are tons of ways to go deeper into regression discontinuity. And so if you'd like to, I would recommend some of the references that I've placed here. These are references that I would describe as advanced for an undergraduate level. But if you dig into them, you will absolutely learn something. So here are some references that are more of the paper style. And then here are some references going more through the Stata code. All right. Hopefully you learned something on regression discontinuity. Be sure to download that do file in the video description to try some of this for yourself. And as you go on from here, try and be finding different places where you see regression discontinuity applicability in the real world. Where are there discontinuities that you can exploit in order to get highly accurate and also very easy to explain estimates of the treatment effect? Thanks so much for watching, and I'll see you in another video.